Hello everybody, thanks for coming to the talk here. I know it's late in the day already. What I'm going to talk about today is association. Just wondering how many of you have heard of association? How many have used it? How many like it? And how many don't like it? And how many would like to use it but don't know enough about it? That's exactly the audience that I'm aiming at today. So hopefully I can convince you there's something useful about it, and you'll start to use it. So what I'm going to start to do, it's a big project association. It's a language-oriented project. People involved in the development, myself. Konstantin, I don't know if Konstantin's in the audience anywhere. Konstantin Kupsov. Tom Wickham-Jones. You might have seen some talks, several releases ago of provisional versions of this. It's been completely rewritten. Stephen Wolfram himself has been a lot involved in the project, particularly in the documentation. Tali, Stefan, who's done a fantastic job helping with the testing. Many other people around the company have helped develop stuff. For example, Brett Champion's group for visualization support. So Stephen is really interested in this association because it's essentially a symbolic list, symbolic representation of a list, and tried to implement something similar in SMP many years ago, but failed. Okay, and that really got to him. And to be honest, the time wasn't really right because they didn't have the data structure that I'm going to be talking about at that time. So, let's look at some significant data structures in Mathematica. Packed arrays in version 4, sparse arrays in version 5, images, graphs that Charles talked about a little earlier. We also have, in version 10, we have mesh regions. I think Rob and Oliver talking about that at the conference. Association that I'm talking about here is a language-oriented data structure, a little bit different to some of these other numerical ones that were added, and something's built on top of association data set, for example, that I believe there's going to be a talk tomorrow on that. So let's just, what is an associative array? Associative array is just a way of storing some pairs of data, a key and a value. Okay, and I want to perform essentially, each key must be unique. I want to perform operations on this associative array. I want to be able to insert, delete, look things up, and then replace values if I decide to. Okay, so here's association, a very simple example. You can think of it as a symbolically indexed list. So instead of using 1, 2, 3, 4 as you would access parts of a list, you can actually use English names or something a bit more. So here's a list, a conventional list in Mathematica. And here's how to construct an association. So you type association and a list of rules of keys and values, and it makes this association object for you. Or alternatively, you can use this syntax here to input it directly. Okay? And then once you've done that and you want to look things up, you can use this symbolic key to get the value of it. Or you can use this symbolic key inside part to get the value of it. Okay, just like you would use part with an index of 2 to get the green out of the list, now I can use association with the English word green to get something out of the association. So you can use it just like a list of rules, but it's more flexible and more powerful. Okay, it uses a similar amount of memory compared to a list of rules, about 30–40% more. It uses 2 or 3 times less memory if you start to use those rules inside replace, okay? Because rules have to build up certain tables internally in Mathematica in able to make them to work fast. So it has a much, much lower memory footprint. It takes about the same amount of execution time to build an association as a list of rules, but continually looking up in association is like looking up in a hash table. It's order 1. So essentially, it's an association. You can think of it like a dispatch of rules, where dispatch would build. Have you used dispatch? Many people use dispatch. When you have a long list of rules, and you want to replace something, it starts to grow. The complexity of substitution starts to grow with the number of rules that you have, so you have to make a dispatch table. So no longer any need to do that. If you use association, the data structure itself is optimized for the substitution. So here's a simple data structure that's not very good for a task, and that's building up a list of primes. If I go through just a do loop every time I find something that's prime Q, and I append it to a list. Every time I append to this list, I make a new list. And I put a new entry in. And so this is order n squared, because it's making a copy of a new list and adding a new entry every time I do some kind of operation. So I need a better data structure to do that. I can either use a linked list, where I use a list of lists and then flatten at the end or something like that. Or I can use something called a linked array. And the interface in Mathematica to a linked array is sow and reap. Okay, they work with intermediary data structures that are better at building up something when I don't know how many operations I'm going to do, but I want to gather information and build it up as I go along. Okay. So just a very quick overview of data structures, trees. Let's just take some English words here and organize them alphabetically. Okay, so I've just, say I've got 7 English words and I build up a tree of those English words, and then I come in and look up, given a word, say appendix, I come in and look up here and I see that it's the string comparison, it's less, so I go to the left. It's greater than this, I go to the right, and then I do a string comparison and find it's equal. Okay, so this is one data structure. The problem with trees is that as you add and delete, you kind of unbalance the tree, and so you need to rebalance it to make the complexity good. So a second data structure, sometimes called also a tree, unfortunately, or called a trie from retrieval. This is similar to a tree, but slightly different. It's optimized for lookup. So now I've split up the English words. I've taken like prefixes as I go through and look up the word. If I go and look up appendix, first I look up the first part of it, then I look up the second portion and the third portion. So essentially I've split up my words into different pieces, and each of these nodes is no longer the full key, it's no longer the full thing that I'm looking at, it's some piece of it. And that makes searching more efficient. And unfortunately, that makes the depth of this tree or the storage of this data structure a little bit bigger. So another one that's very nice, that we use a lot internally in Mathematica, is a hash table. And the nice thing about this, it's not specific to strings. When you hash, you build an integer number that corresponds to any expression. Okay, and that single integer number is then used to insert your expression into a table. So let's take these English words again, and let's make a character hash. Let's jumble around these characters and give them numbers and shuffle the bits around and make an integer number. And then let's take a hash table of prime size, usually. Here I've got a table of size 13. And let's put these English words into this hash table. And you can see that when I take the actual hash values, which are 64-bit values, mod some size of the table, that tells me the index that I need to go and look up that particular English word. Okay? And the nice thing is that insertion and deletion into this table is order 1 now. Now the problem is with a hash table is as it grows up and fills up, it needs to be rehashed. It needs to be resized. Okay, so we use a strategy like doubling the size of the hash table. You have to keep track of the load of the hash table. Just as trees, you had to balance them. And that's not good for a real-time system. In a real-time system, you want the execution time to be nice and smooth. If you suddenly have to freeze the system and then go and double some array and then copy everything over, that's problematic. So it's good because it's order n. You need to resolve collisions. Sometimes when you make an integer number from 2 keys, they go to the same integer number. So you use some collision strategy, chaining or linear probing or something like that. It requires that you have a good random mixing hash function. And as I said, it's not so good for real-time systems. So this is the data structure on which association is based. It's kind of a mix of all the things that I've just talked about. In particular, trie or trees and hash tables. It's a hybrid of the two things. It's a relatively young data structure. It's appearing a lot now in functional languages. Clojure, that's used by JavaScript, Haskell, OCaml, Ruby Scala. There's a C++ and a C# implementation. A lot of these are experimental codes, not complete, still buggy or whatever. The former ones are the ones that are the most complete and the most used. They're also taught in some graduate classes. I found some nice lecture notes here from Penn State University that talks about this data structure. The nice things about this, it's a very good general purpose data structure, jack of all trades data structure. It might not be as optimal in every single case, but it's close enough to be good enough for most uses. So how does it work? Well, if we just take a string and we make a 64-bit number, a hash value for this string, okay, then what we do is we chop up this hash number into blocks of bits. Okay, we chop it up into blocks of bits. And then starting with these blocks of bits, we use each single block as an index into some tree structure. Okay, so the first block of bits would be the index into an array at the first level of the tree, and the second block of bits would be the index into the second level of the tree, and the third block of bits an index into the third level of the tree. So it looks something like this for the example that I have. Here are my English words. Here are the first blocks of the hash values of these English words, and here are the second ones. And the data structure looks like this. This is the root node. And here I've used blocks of 8 bits. So each node here has an array of size 8. Okay? And if I go, say, 7 and then 4, then I get the word append. Okay? The word. So this is the first index of this array, the red. And then the green is the second level when there are 2 entries, 2 or more entries here. So there's a 6 and a 6, so I need a second index to resolve the uniqueness of those things. Okay? So this is a way of kind of combining a tree and a hash table. Can anyone see a problem with it? It's a bit bloated. Okay? All these X's are empty nodes. Okay? So we have a similar kind of problem to a hash table. It's not completely filled up. So the missing link is to try and come up with a sparse representation of that node. Okay? And the way that you do that is to take each index and pack those indexes of those arrays as bits into a single integer. Okay? And that single integer is called a bitmap. And that bitmap then represents only the positions that are non-empty in that previous array, okay, each level of the tree. So let me just show you that example again. This is what the bitmapped tree would look like. Okay? So now I have only the nodes which actually contain the words, and inside this contains an array now, but the array only has exactly the number of elements that I need to resolve in my data structure. And inside each of these is a bitmap array. If I have index 7, then I shift to see if the 7th bit is active or not. If it is active, I know it's in the tree, and I can go down the tree and look up some value in my data structure. So why go from a hash table to this other data structure? That's the big question. So why these functional languages? Why are they so interested in this other data structure? And the reason is persistency and data sharing. Okay. So I have a big hash table with a lot of information in it, and I want to just add one entry to that hash table. But I want to keep a copy of the old hash table, right? I have to clone the entire hash table and just add one entry. And say you've got 1 million or 10 million or something like that elements. That's a lot of data copying. These databases get bigger, et cetera, et cetera. So what I want is some kind of data structure where I can freely add to it or subtract from it, but not to destroy too much the structure that's that's already there, or the information that's already there. I want to sort of maintain that copy, but just modify it enough that I can also store the new information. So here are my English words again. And what I've done is I've just added one at the end here. Okay? And I have a little picture. Oh, that might have to just squeeze up a bit here. Okay. So this is my original data structure containing my original words here. This B, all this part here. Okay. And then I have added this word. I've added this word here. In here. Here it is. Applied. Where did it go? Oh, sorry, that's here. That's a typo, excuse me. So applied is in here, okay? And in order to insert this new node, what I have to do is I have to make a new root node, and I have to make a new node at node 7 here. And then I set pointers in this to the existing data and to the new data. But this is just sharing what was already there in the previous data structure. So I've kept my previous data structure, and I've added just a couple of nodes and a new entry, and these just point now to the existing data. Okay? So instead of having to copy every single node and every single entry in this original data structure, I've just added a little bit here that allows me to store something new but maintain something old. So the association is a group of nodes that essentially model something like a hash table. And it dynamically converts and unsparsifies to this array format or sparsifies to this bitmap format automatically inside. Okay, so let me just give you one or two examples. Yeah, so I want to make an association. That makes this association object. And then I want to look up, I want to say, inside an association, is the key that corresponds to the symbol A2, is that present in my table? And I get true. And I get true without having to go through, in a list of rules, I'd have to go through sequentially each one of these to try and find out if this key was present. In this data structure, I don't. It's like a hash table. It's just automatic. It's independent of the number of rules that I have here to find out whether this key is present or not. Okay? And similarly, if something is not present, then I can get that information very quickly. And likewise, I can find information about whether the actual value, the right-hand side of these rules, whether something is contained in association or not. There are a lot of functions in Mathematica that have been completely rewritten and support association just like they support lists. So it's a fundamental data structure that's been built in at the lowest level. So since I'm kind of pushing on for time here, I have a lot of examples. Let me just kind of give you one that was a motivating problem for implementing association in the Haskell language. Okay, this person Tibble was doing Twitter data analysis. He's computing a communication graph from Twitter data and scanning it daily to allocate what he calls social capital to nodes. You know, people are behaving well, they're making good constructive comments on Twitter, or they're behaving badly and making very negative comments or whatever. And he gets this graph from 100 million tweets, collecting this information daily, and the graph has about 3 million nodes. And he needs a data structure that's fast for doing this kind of thing. So here's my little model to do this kind of thing in Mathematica. So essentially I've made like a sparse banded array that gives me control over the shape and the communication that goes on in this kind of community. Okay? So just to make things simple for this talk, I've just taken 10 nodes with a bandwidth of the sparse array of above 3 and above and below the diagonal, so there's kind of a limited communication between groups of people. But this easily hundreds of thousands or millions of nodes is not a problem to extend to. And then these are now users on Twitter. And it's a directed graph, so user 1 tweets user 4 and is tweeted in fairly negative comments here, so it's assigned a value of -22. But number 4 tweets back in a fairly constructive way, so that's given like a positive comment with a weight of like 39. Okay, So let's see if we can do any actual analysis on that thing. I'm going to make a bunch of community graphs for a week of data, okay? And then I'm going to build a bunch of associations. I'm going to get the adjacency matrix from each of those graphs, and I'm going to make a bunch of associations that connect the users with their Twitter daily totals. Okay? So that is the sum of all the tweets that I sent out, the sum of all the weights of all the tweets that I sent out. And then I'm just going to plot it. So I just feed here I build up a list of associations, one for each day, and I just give it to list plot. And it looks like this. So the peaks are, you know, positive comments on a particular day from users, and the troughs down here are someone who tweeted, you know, very negatively overall, okay? And it could do a similar graph of tweets received by somebody to see if somebody's particularly, you know, being targeted. And the point about the association is, well, I can use it I can just take my list of associations and I can say, well, how was user 9 doing during this 1 week period? And here's his kind of tweet total, yeah? So started off a little bit negative, got very constructive around the 3rd day, and then kind of got a bit bitter and twisted towards the end and started maybe Friday, I don't know, Friday, Saturday, Sunday, had a bad weekend, started kind of tweeting in a fairly negative way. And I can just use position, min, max, all of the kinds of functions that you use on lists, on associations, and I can find out, well, the worst tweet total during the entire week was on day 3, and it was by user number 3, okay? And I could obviously use an association to map indices to names, to hide, you know, names of particular. I was actually going to use names of developers here, but I thought, well, you know, if I said Dan was tweeting negatively on day 7, he might get offended or something. So I thought, well, I better just use numbers here. And this is, you know, a very positive, user number 9 made the most positive contribution on the 3rd day. But let's look at the, so here I can just, you know, just use normal functions to analyze my associations, like mean, the rounded mean, and I see like this is the average over a 7-day period of the tweet, the tweet total for somebody, and I see like user 6 has been, you know, pretty naughty during this week. He's got a minus 50 tweet total. Somebody might want to send him an email just saying calm it down a little bit or something. These 2 users on the average have been, you know, fairly good. So we might want to say, well, you know, you've been contributing well to the community or something. Motivate them in that way or whatever. Okay. I was going to talk about this, or let me just go to the summary. Okay, I'll just go straight to the summary. So association. Didn't have that much time to give you too many examples. I wanted to explain what it is. It's a data structure, essentially, that allows you to do operations on things in a more flexible and more powerful way than a list. It required a considerable amount of infrastructure. We have a separate garbage collection. It's probably the most complicated data structure in Mathematica. Some of the methods for sparse arrays or whatever, they're more complicated. But as a data structure, it's probably the most complicated data structure. We had to make lots of improvements to existing functionality, hashing itself. We had to make rules a little bit more lightweight in terms of their memory footprint, etc. And lots of ongoing things that we're working on, minor bug fixes, new functionality, and improving performance of this data structure. So I hope that's given you some insight, and I hope it's stimulated you a little bit to kind of, you know, take a look into association. And if I'm around, you know, the whole conference, if you want to talk to me about, you know, functionality that's missing or things you'd like to see or uses that you're thinking of or whatever. Okay.